Hello, everyone. Today we are going to talk about a special type of limits, which is called indeterminate forms, and the rule how to calculate these limits, which is called L'Hopital's rule. So first, we are going to start with definition. Definition: limit of the ratio f of x over g of x as x approaches a is called indeterminate form. When f of x and g of x approach 0 as x approaches a. So guys, basically we do have a indeterminate form, which is a limit between two functions, ratio of two functions, and each function by itself approaches 0 when x approaches a. By the way, a can be not only the number, but also infinity. And that's going to be indeterminate form 0 over 0 if each of these two functions is approaching 0. Uh, Let me write it. Type 0, 0 type. Let's consider a couple of examples, and we are going to start with examples we already kind of know. Let's imagine limit x squared over x plus x approaches 0. It's a fraction, right? Each numerator and denominator approach 0 when x approaches 0, so we are going to have 0 over 0 form. Well, if we look at this limit from like position of knowledge we already have, if we divide x squared over x, and we are going to have actually, what is going to happen actually? Actually, the limit is equal. We simplify it, we get x as x approaches 0, and when x approaches 0, x approaches 0. So this limit is equal to 0. So that was my first limit. Second limit, another indeterminate form of 0 over 0. Let's put now x squared in denominator. Well, still, we do have 0 in numerator and 0 in denominator when x approaches 0. It's not always 0 over 0, just like when x approaches 0, right? But actually, what is going to be the limit? Limit is going to be equal if you simplify it. So 1 over x as x approaches 0. We know that depending on which side it approaches 0, it can be either positive or negative infinity. I'm going to put plus minus infinity because I did not specify on which side x approaches 0. Remember that if you do have 0 over here, you can approach on this, and that's going to be left, and you can approach over here, and that's going to be right. Usually we mark plus or minus as a little index next to 0, right? So you see that determinate forms 0 over 0 can result in 0, can result in infinity. And so they can result in something like a just regular number. Let's consider another one, just as example. So you see all different possibilities. Here again, maybe I'm going to approach infinity here. Remember that a here is not necessarily supposed to be a number. It can also be infinity. And I'm going to consider function x squared minus 1 divided over 2x squared plus 1. Well, again, when x approaches infinity, well, this one actually is going to give us infinity over infinity, so maybe we should not do it yet. Let's do something else. I want to do infinity over infinity. Next explanation. Let's do this. Okay, sorry. Let's do more of like 0 over 0 first. How do I turn on the razor? That's a mistake. Oh, sorry. No, I don't need a square. Sorry, guys. I'll need to delete all this stuff. Okay. Let's consider this limit. Limit as x approaches 0 of sine of x over x. Well, guys, in calculus 5a, we learned that this limit is actually equal to 1, right? Is it 0 over 0 in determinate form? Well, sine goes to 0 when x approaches 0, right? And the denominator also goes to 0, so this is indeterminate form 0 over 0, but actually we do know that limit is equal to 1. Let's say from calculus 5a, right? Still remember that's one of the limits we started working when we did the sine derivative. Okay, so you see that indeterminate form 0 over 0 can be equal to 0, can be equal to infinity, and can be equal to 1 or some other number. These three indeterminate forms were easy to kind of simplify and find out like what is the result. But what if we have a question looking like this? What is going to be the limit of ln of x over x minus 1? And x is going to approach 1. First, let's check, is it indeterminate form? Remember how ln looks. Ln looks like this. Let me remind you, that's a graph of ln goes to the point 1. So you raise any base to the power of 0 and you get 1. So actually at 1, when x approaches 1, ln is equal to 0. 1 minus 1 is also going to be equal to 0. So we do have indeterminate form 0 over 0. But we do not know what is going to be this limit, ln of x over x minus 1. That's where we need a special L'Hopital's rule to actually figure this out. And that's what we are going to learn in this class. I'm not going to prove in the theorem of L'Hopital's rule. I'm just going to give you the rule. Uh, so L'Hopital's rule. Consider two functions, f of x and g of x, differentiable. And the derivative of the bottom is not equal to 0 on open interval I that contains x. That contains x equals a, excluding possibly point A itself. And limit of f of x as x approaches a equals 0. And limit of g of x as x approaches a also equals 0. Or limit of f of x as x approaches a equals plus minus infinity, and limit of g of x as x approaches a equals plus minus infinity. I did not consider any examples of infinity, but we are going to have them later when we introduce the rule. So these are going to deal, the rule is going to deal with indeterminate form 0 over 0 or infinity or infinity. It doesn't matter, like the sign of infinity. Then, like now the rule itself, then limit f of x over g of x as x approaches a is going to be equal to the limit of f of x derivative and g of x derivative as x approaches a. And of course, limit is supposed to exist, or it can be equal plus minus infinity. Okay. Um, let's apply this rule to our question D. Remember, question D was limit of ln of x minus 1, as x approaches 1. So, well, we already know that ln is equal to 0 and 1 minus 1 is equal to 0 too. So we do have indeterminate form 0 over 0. Guys, when we solve problems like this, we'll need to specifically tell that we do have the form. The first, we need to check if it's 0 over 0. If it's not 0 over 0, but for example, 2 over 0 or 0 over 2 or 2 over 3, we're not going to use the rule. The rule is used only when 0 over 0 or infinity over infinity. Now, guys, after that, you need to tell that you are using L'Hopital's rule. Well, you're not going to use a whole name of L'Hopital. So you're going to put L and then little comma and then H. And then let's use L'Hopital's rule. L'Hopital's rule tells that we'll need to calculate the limit x approaches 1, but derivative of numerator, which is 1 over x, right? And derivative of denominator, derivative of x is 1, right? And derivative of minus 1 is 0. So here, guys, we can just calculate this limit by plugging in 1, right? 1 over 1 over 1 is equal to 1. So this indeterminate form actually is equal to 1. So this limit equals to 1. Same as like sine limit. Remember, sine of x over x. Well, that's how to use a rule. And of course, we are going to apply this rule to different cases. Sorry. Oh, I pressed something and my whiteboard is moving. Second. Okay, let's consider another example. I'm going to label it as example, I don't know, 2, for example. This was example 1. Let's consider a limit of sine of x over 1 minus cosine of x as x approaches pi from the left. See the little minus over here that's approaching from the left. Wow, let's plug in this pi into sines. Sine of pi is equal to what? To 0, actually. Now let's check denominator, because if we want to use L'Hopital's rule, we need to make sure that both numerator and denominator either infinities or zeros. What is cosine of pi? Wow, we know that cosine of 0 is equal to 1, cosine of pi is equal to minus 1. So we do have 1 minus negative 1 in denominator. And we are going to have over here 2, 1 plus 1, 2. What is going to be the limit then? The limit is equal to 0. We are not going to use L'Hopital's rule here because this is not indeterminate form. Remember, guys, you always need to check it because sometimes the limit can be calculated without using L'Hopital's rule. Just standard limit laws. Okay, now I'm thinking to consider example 3, which is going to be infinity case. Example 3. Limit as x approaches infinity, ln of x divided over square root of x. Well, we know that logarithm goes to infinity. When x goes to infinity, square root also goes to infinity. I'm going to just draw logarithm graph and the square root graph, and they both go to infinity. So we know that ln goes to infinity, not very rapidly, but goes to infinity. Square root goes to infinity too. So we do have infinity over infinity indeterminate form. We can use L'Hopital's rule. Again, guys, whenever you use L'Hopital's rule, let me know that you are doing this by using L and H, okay? So L'Hopital's rule means that you will need to differentiate numerator separately and denominator separately. Numerator is going to give us 1 over x. We'll already kind of remember. Denominator, the square root is, derivative is 1 over 2 square roots, right? You can use, you know, the power rule over here and write down like it's x to the power of 1 over 2, but like I already remember the derivative. So here, guys, we are going to simplify this expression. And when we simplify it, we're going to have, like, remember, when we divide by fraction, we multiply by inverse. So we have 1 over x multiplied by 2 square roots of x over 1, right? As x approaches infinity. And here is x and here is the square root of x. If we cancel square root of x, we are going to have a limit of 2 over square root of x. And when x approaches infinity, it's going to bring us to 2 over infinity, which is going to be equal to 0. So this limit is equal to 0, though it was infinity over infinity. Okay, so that's how we calculate limits like this. Sometimes you will need to use L'Hopital's rule several times. If you kind of differentiate it and you still get infinity over infinity or 0 over 0, you can use it second time, because actually L'Hopital's rule doesn't care if you are kind of having functions or derivatives. Derivatives are functions too. You know, they are just derivatives to other functions, but by themselves they're functions too. So that's how we use it for ratios or fractions. Now, we are going to move to indeterminate products. Let me make it a little bit bigger. Indeterminate products. Indeterminate products are a little bit more complicated, and they are going to look like this. Limit of f of x multiplied by g of x. And here, guys, it's not going to be like both zeros or both infinities, because in this case, the limit is either 0 or infinity. Here, we are going to have one function going to 0 and one function going to infinity. So I'm going to write it down symbolically as 0 multiplied by infinity. I don't know which one is going to do 0, which one is going to do infinity. But the idea here is to represent this product as a fraction, and either like fraction looking like this, f of x divided over 1 over g of x. If we simplify this, we are going to kind of multiply it by g of x over 1, which is going to give us a product, right? As x approaches a. Or as a limit of g of x over 1 over f of x. Unfortunately, L'Hopital's rule does not tell us specifically what to put down in denominator, what to put in numerator. But basically, guys, the idea is to reduce it to the 0 over 0 or infinity over infinity. For example, if f is 0, then 1 over g, if g is infinity, is going to be 0 too, or infinity over infinity in this case. If g is infinity, then 1 over 0 is going to give us infinity. And then apply L'Hopital's rule, standard L'Hopital's rule to this expression. I'm going to show you an example. So I think example number 4. Let's consider a limit of x multiplied by ln of x. Looks like we are heavy on ln now. It's going to be x approaching 0 plus. Why 0 plus? Because ln actually is undefined on the left from 0, right? It's only defined on the right from 0. So what are the numbers here? Well, when x approaches 0, it's approaching 0, right? ln, if we go back to ln graph, approaches negative infinity when x approaches 0. So we do have the 0 multiplied by infinity. Now the problem is, how do we consider, like, how do we turn it into fraction? Let's try to turn it into fraction next way. Limit ln of x divided over 1 over x. The idea is to modify this expression into a fraction, which means that you just need to flip over one of the factors. What do we have? We have on numerator, we have negative infinity, right? In denominator, 1 over 0 is going to be, next to 0 is going to be positive infinity. And we do have infinity over infinity. We can use L'Hopital's rule, right? Let's try. Don't forget to write down that L'Hopital's rule. So derivative of ln is 1 over x, right? And derivative of 1 over x is negative 1 over x squared, right? And x approaches 0 plus. I'm going to continue and move to the next slide. So let's simplify this fraction. We are going to have limit of 1 over x. Now we are going to multiply it by x squared over 1 with minus x approaches 0 plus. And let's simplify square and x, and we are going to have a limit of negative x as x approaches 0 plus. Well, it's not very important, like minus or plus, so we are going to get 0 here. And that's our limit. The question is why I decided to do it this way. What if I decided to do it opposite way? What if I decided to put ln in denominator? Here, guys, I'm going to tell you rule number 1. Never put ln in denominator. But let's do it. I'm going to use red color and just to show you what is going to happen if you kind of decide to keep x in numerator and put ln in denominator, how it's going to work. And where, guys, you are going to know that you are doing it wrong. And it's not bad to do something wrong. And again, we just represented our fraction, our product as a fraction, and x approaches 0, right? ln approaches infinity, 1 over infinity is also 0, so we do have actually indeterminate form. Let's use L'Hopital's rule on it. Derivative of x is 1. Perfect. What is derivative of 1 over ln? Well, their composition, right? It's 1 over x, and then ln as x, and we're going to get 1 over ln square of x, right? Because when we differentiate 1 over x, we are going to get a 1 over x squared, like over here, right? And then we differentiate ln, which is going to also give us 1 over x. If we simplify this expression as x approaches 0 plus, we're going to find out that limit is going to be, if I simplify it, means that I bring all this from denominator into numerator, minus x by ln square of x. X approaches 0 plus. Do you see, guys, that we started with this limit, x by ln, and we kind of made it more complicated. Now we have ln squared, so we did not simplify it. At this point, you're probably supposed to feel, maybe my fraction is not correct. Maybe I should use other way. There are always two ways. Eventually, you are going to know which way to use. But for first 3-4 examples, you can try both ways. And if you see that, yeah, my way goes nowhere, well, try other way. You see, usually one of them must work, and one of them is not going to work. Well, and also, special rule, do not put ln in denominator. You see what happens when you differentiate ln? The expression is becoming much, much worse. I mean, when you put it in denominator, if you just differentiate ln, it's very nice, 1 over x, right? But if you differentiate 1 over ln, that's just a nightmare. Okay, so good. So we know how to use L'Hopital's rule for ratios. We know how to use L'Hopital's rule for products. Now let's learn how to use L'Hopital's rule for differences. For differences, again, the rule is going to be reduced to the fraction. I'm going to write down indeterminate differences. And I'm going to write down in general what we have. X approaches a. Difference is f of x minus g of x. And you can have, for example, f of x going to infinity and g of x going to infinity. Just like a question is going to be infinity minus infinity. What is going to be the answer? Let's consider example, because again, the differences, products, and fractions are all supposed to be just fractions. Let's consider example. And usually all differences must be reduced to fractions. There is no other way to use L'Hopital's rule on them. X approaches pi over 2 from the left, and I have secant of x minus tangent of x. That's a difference. Well, guys, you probably don't remember the graph of secant and tangent. I'm going to remind you maybe over here. So how the tangent looks first. Tangent looks like this, all right? This is pi over 2, and the left of pi over 2 is going to be this side, so that's infinity. How secant looks? Okay, that's tangent. And again, I'm not doing the whole graph because, well, I'll just need 1 point, but if you remember how it looks, that's fine. Secant is built on cosine graph, right? Remember how do we build a secant? We build cosine graph, and then we do vertical asymptotes where the graph intersects 0, and then attach the graph of secant to the maximum of cosine. Well, we just need 1 point. My secant goes to infinity also as x approaches pi over 2 from the left. So we do have infinity over infinity. Let's try to turn it into a fraction. The simplest way here is to go back to original definition of secant. Secant is what? 1 over cosine of x. And the original definition of tangent is sine of x over cosine of x. And let's try to simplify this fraction, and eventually we are going to get one bigger fraction. So what we have, limit as x approaches pi over 2 from the left, and in numerator we have 1 minus sine of x, and in denominator we have cosine. That's a common denominator already. Now at pi over 2, we know that cosine goes to 0, right? At pi over 2, sine goes to 1. So we have 1 minus 1, also 0. So we are fine. We have 0 over 0. We can use L'Hopital's rule. And let's do differentiation. So what is derivative of 1 minus sine? Well, derivative of sine is what? Cosine with minus. Minus cosine of x. What do we have in denominator? In denominator, derivative of cosine is minus sine of x, right? X approaches pi over 2 from the left. Now, minuses cancel. Cosine over sine is what? Well, we even don't need to kind of consider cotangent. We just know that at pi over 2, cosine is equal to 0 and sine is equal to 1. We have 0 divided over 1, which is going to give us 0. So the limit is going to be equal to 0. Okay? Well, guys, this section about indeterminate forms is very long, and I think I'm going to make 2 videos for it. So for this video, I'm going to be done, and I'm going to make a new video for indeterminate powers, because powers are kind of long too, okay? So I'm not writing down the problems to solve. I'm going to give them at the end of that video.